Hello everyone, this is lecture 8. So in this lecture, we're gonna look at another application of matrix operations. So basically, we're gonna use matrix multiplications to encode and decode messages. Okay, so let me write the definition of cryptogram, right? So it's related to cryptography. So you have a message, you can encode that, or you receive a message, you can decode that, right? And the messages in general is called cryptogram, right? So a cryptogram is a message written according to a secret code so a cryptogram is a message written according to a secret code. One method is to use matrix multiplications to encode and decode messages. Okay, so what we're going to do is we have a table, the alphabetical table, and we're going to set that the letter A corresponding to the number 1, letter B corresponding to number 2, so on and so forth. The spacing between the words going to be either 0 or 27, right? So in this case, we can also set that 27 equal to some spacing, right? So we're gonna need, so that's the setup, right? So either 0 or 27 is the spacing. All right, so the first thing in this example basically is to just write the uncoded message into the row matrices. Okay, so you have the message of meet me Monday, right? So what you can do is you partition the message, right, including the blank space or the spacing between the word, into a groups of 3. Why group of 3? Because you want to uncoded the row matrices of the size 1 by 3. Right? So you can partitioning the message, right, including blank space, but ignoring punctuations, into groups of 3, right? Again, because the requirement is you break this message down to the matrix of 1 by 3, right? So you have the message meet me Monday, right? So you can break this down into MEE, and then T spacing M, and then you have E spacing M, and then O and D, and then AY, and then the last component of this last row matrix is a spacing as well. So there's some spacing in at the end. Okay, so now for the letter, you compare the letters with the corresponding numbers that we already make the assumptions here. So M corresponding to 13, E corresponding to 5, T corresponding to 20, so on and so forth. Now, in this case, we're going to try the spacing with a 0, right? So later on in this example, we're going to have the spacing of 27. right, later on in this lecture. So this message can be encoded into a row matrices as follow, right? So the word MEE is going to be 1355. The next row matrix is going to be T space M or 20013. Then the word E spacing M is 5013. The next word O and D is going to be 15, 14, and 4. And the last row matrix is going to be 1 corresponding to A, 25 corresponding to Y, and 0 again to fill up the missing entry, and that will stand for the spacing of the word. Okay, so you have the word meet me tomorrow, and you put this into a 1x3 row matrix. Okay. Now you're going to encode this message, right? Because you don't want to have a one-to-one corresponding of the word and the number. Is very easy to break, right? So you have to encode the message somehow. In a way, you have to write the secret code for your message. Okay. So what you can do is you're going to use this matrix. So this is the 3x3 matrix, right? So what we can do is we have 3 different part. So the uncoded row matrices, that what we already have in the previous example. We have something called the encoding matrix A. All right, so that is given to us as well. And the coded row matrix, right? What we do is we're going to take the uncoded row matrices, multiply with the encoded matrix A to obtain the coded row matrices. Okay, so the first uncoded row matrix is 13, 5, 5. So this is right, the first row right here, and you multiply with the matrix A, the encoding matrix, which is 1, -2, 2, -1, 1, 3, 1, -1, -4. And if you do matrix multiplications, right, so the first entry going to be, you take this row and multiply with the first, or combine with the first column of matrix A. And the first entry will give you 13, right? Let me double check this, right? So this is 1x3 matrix. This is 3x3 matrix. And therefore the coded row matrix has to also be 1x3 matrix as well. Okay, so this is the first entry. The second entry is that you take this row and you combine with the second column of matrix A, and the calculations give you -26. And the last entry is that you take the row, this row matrix, and combine with the last column of matrix B, and you get the answer to be 21. Okay, so this word get coded up and give you this row matrix. Okay, now you're going to do the same for the rest of the uncoded row matrices. All right, so the next row matrix that we're going to play around with is 20, 0, 13, multiply with 1, -2, 2, -1, 1, 3, 1, -1, -4, and you get the row matrix of the form 33, -53, -12. Okay. The third row matrix is 5013, right? So corresponding to this part of the message, you multiply this with the encoding matrix. So let me just make a copy of this matrix, right? And you do matrix multiplications one more time, and you receive a row matrix of the form 18, -23, -42. The fourth row matrix is 15, 14, 4. And you're going to multiply with this encoding matrix one more time. Give me the row matrix of the form 5, -20, 56. Okay. And then the last one is 1, 25, 0. Let me copy this matrix one more time. Let me space this out. And you get the row matrix of the form -24, 23, 77. Okay. So you have a message, and you break that message down into row matrices. Okay. And then you use kind of a key, right, or encoding matrix to change or to transform this message into a coded row matrices. Okay. So now what you receive at the end is that, so the sequence of coded row matrices is, right, so you have 13, -26, 21, 33, -53, -12, then 18, -23, -42, then you have 5, -20, 56, and the last row matrix is -24, 23, and 77. Okay. And to make the message more secretive, what you do is you remove the matrix notations, right? So removing matrix notation, produce the cryptogram. Okay, so the message is 13, -26, 21, 33, -53, -12, 18, -23, -42, 5, -20, 56, -24, 23, and 77. Okay, so if you receive this message, you can actually reverse engineer and obtain the original message, right? So if you receive this number, they need to give you the key. Without the key, there's no way you can transform this this sequence of number back into the original message, okay? Or if you get this line of sequence of number, then it's very easy to recognize the one-to-one correspondence of the letter and the number, so they can break the message or break the code very easily. So you need to encode this into a different row matrices. Right? Okay. So what if you receive this line of sequence of number? How could you break that? How could you decode that cryptogram? Right. Again, you need a key, and the key is the matrix, this matrix, right? So very similar matrix that we just work with. Okay. Right. So in this example, this is forward directions. You have a message, you want to code that up to obtain this cryptogram. Now, if you receive a cryptogram, how would you turn that back into the message that you want to read? What you do is you're going to find the inverse of this matrix and then use again matrix multiplications to obtain the original matrix, the original message. Okay, so how could you find the inverse of this 3x3 matrix? Again, you can use the Gauss-Jordan elimination method that we learned in lecture 6. You can perform elementary row operations to obtain the inverse of the matrix A. Another way to do that is, of course, to utilize Python and then form the form the augmented matrix, and then use the reduce row echelon form command to help you with the inverse of the matrix. Okay, so that's what I'm going to do. So first, we need to find the inverse matrix of A, right, by using Gauss-Jordan elimination method. Okay, so the augmented matrix is so you get the matrix of the form. So one side is 1, -2, 2, -1, 1, 3, 1, -1, -4. This vertical line, you have 1, 0, 0, 0, 1, 0, 0, 0, 1. And of course, you're going to perform the elementary row operations to obtain the inverse of the matrix, right? So after the elementary row operations, this is what you're going to get: 1, 0, 0, 0, 1, 0, 0, 0, 1, vertical line, and the matrix of the form -1, -10, -8, -1, -6, -5, 0, -1, -1 again. Okay, so this is multiple step of elementary row operations. But again, you can form this augmented matrix in Python and use the command rref to help you with this calculations. So that's what I'm going to do. So again, basically what I'm doing is in lecture 6, we already have the code. We're just going to copy the code from lecture 6 and paste that into lecture 8. Change the augmented matrix and then let it run and see what we get, if we get the same answer here. Okay, let me turn to the code. All right, so here's the setup again. So this is the lecture note. This is Jupyter Notebook. As you can see, this is from lecture 6. What I'm going to do, I'm just going to make a copy of this code and just paste that into a new Jupyter Notebook. And I change this into lecture 8. Okay, so everything's going to be the same, except that I'm going to change the augmented matrix into this, this one. Okay, so the first row is 1, -2, +2, 1, 0, 0. The second row is -1, 1, and +3, and also 0, 1, 0. The third row is 1, -1, -4, and then 0, 0, 1. And I'm gonna, everything else going to be the same. Not gonna make any other changes at all, except for the augmented matrix. Now you just hit Shift Enter. And let's see what we got here, right? So the first row is 1, 0, 0, -1, -10, -8. So that's corresponding to what we have over here. Then the second row is 0, 1, 0, -1, -6, -5. right? It's the same with what we have in this reduced row echelon form. And the last row is 0, 0, 1, 0, negative 1, negative 1. So it's the same as well. So we obtain the inverse of the matrix A. Right? So the inverse is of this form. Okay. So now to decode the message. So to decode the message, we go into partitions, the message into groups of 3, because the matrix you received is a 3 by 3 matrix, to form the coded row matrices. Okay, so this is the cryptogram that you receive, right? So we're going to break it into the group of 3, like this. Okay, and so let me write those over. So again, what we have is coded row matrices, right? That's what we form up here. And then the second part of this calculation is the decoding matrix, right? And in this case, the inverse of A, or A inverse. And then we do the matrix multiplication between these two matrices, and you're going to receive the decoded row matrix, or row matrices. Okay, so the first row, the first coded row matrix is 13, negative 26, and 21. You multiply with the inverse of A is negative 1, negative 10, negative 8, negative 1, negative 6, negative 5, 0, negative 1, negative 1. Right. And again, do the matrix multiplications. So this row matrix combined with the first column of matrix A inverse will give you the first entry of decoded row matrix, which is 13. Now for the second entry, you take this row matrix and combine with the second column of A inverse to get 5. And for the last entry, you take this row matrix and combine with the last column of A inverse to get 5 again, right? And we continue doing that for the rest of the coded row matrices. Okay. The next coded row matrix is 33, negative 53, negative 12. You're going to multiply this with A inverse, negative 1, negative 10, negative 8, negative 1, negative 6, negative 5, 0, negative 1, negative 1. And you get the decoded row matrix of the form 20, 0, 13. Let me add one more page here. Right. And the next coded row matrix in the list is 18, negative 23, negative 42. You multiply with A inverse. So let me make a copy of A inverse. And you get the decoded row matrix of the form 5, 0, 13. Right. The next coded row matrix is 5, negative 20, 56. Multiply with A inverse. And you get the decoded row matrix of the form 15, 4, 4. And the last row matrix that we need to deal with is negative 24, positive 23, 77. I'll multiply with A inverse. And you get this equal to 125, 0. Right. And from here, you say that the sequence of decoded row matrices is so 13, 5, 5, 20, 0, 13, 5, 0, 13, 15, 14, 4, and 125, 0. And you will match this message or this number with the table that we get up here with the alphabetical table, right? So the one-to-one corresponding that A corresponding to 1, B corresponding to 2, so on and so forth. And you will get the message of mid-May Monday again. Okay. And of course, in practice, you need to know the key. You need to know the matrix. Without knowing the matrix, there's no way you can break it. Okay. Now, we're going to decode another message. Now you receive this cryptogram, and you receive the matrix of this form 3, 2, 1, 1. You need to know one thing, that when you deal with the decoding matrix or coded of the message, there are sometimes the row matrices will work. Sometimes column matrices will work, so that increase the level of secrecy that you want to deal with. Right. So in this case, in this particular example, the row matrices will not work, but the column matrices will work for you to decode the statement or the cryptogram. All right, so because you want to decode the statement, what you do is to find the inverse of matrix A. First, find the inverse of matrix A. All right, so you form the augmented matrix of the form. Right, so 3, 2, 1, 1. Vertical line. This is 1, 0, 0, 1. Okay. And then you perform the Gauss-Jordan eliminations method or the elementary row operations. And we're going to get 1, 0, 0, 1. This is 1, negative 2, negative 1, 3. Okay, so either, of course, again, you either use elementary row operations to obtain the reduced row echelon form of the augmented matrix by hand, right? Or you can use Python to help you with the calculations. So you can go back to Python and try if you can obtain the same result here. Okay. Now to decode the statement, right? What you do is you partitions the message into group of 2. To form the coded column matrices. All right, so now you partition into a group of 2 like this. Okay, and you turn this into into column matrices. So you get, this is 64 and 23. The next one is 102, 41. The next one is 82, 32. Next one is 97, 35. And then you get 71, 28. And the last column matrix is 69, 32. Okay, you partitions the cryptogram or the message that you receive into the group of 2 to form the coded column matrices, right? And then you're going to use the inverse matrix, right? Or apply the inverse matrix on these column matrices by using matrix multiplications. Then what we do is gonna take the inverse matrix of the form. Right, so this is the inverse matrix: 1, -2, -1, 3. So 1, -2, -1, 3 to multiply with 64, 23. Right. And you receive another column matrix of the form 18, 5. Right. And we're going to do the same for the next column matrix. Right. Apply the inverse matrix on the column column matrix 102, 41 to get the column matrix of the form 20, 21. Then inverse matrix 1, -2, -1, 3 multiply with 82, 32. This is equal to 18, 14. The next one is 1, -2, -1, 3. You multiply with the column matrix of the form -7, 97, 35. This is equal to 27 in 8. And the last one, the next one is 1, -2, -1, 3. And multiply with 71, 28 equal to 15, 13. Right. And the last column matrix is 1, -2, -1, 3 multiply with 69, 32. Okay, and you get the column matrix 5, 27. Okay, so you have a cryptogram, you have the key, which is the matrix, the 2x2 matrix of the form 3, 2, 1, 1. To decode this statement, you need to find the inverse of matrix A. This is the inverse matrix you obtain. And then you do matrix multiplication, take this inverse, multiply with the column matrix of that you form from this message, right? And this is the decoding message or decoding column matrices that you obtain after this matrix multiplications. Now you go back at the beginning and look at this alphabetical table, and you find a one-to-one corresponding between letters and numbers, and you will find that. So 18 corresponding to letter R, 5 is letter E, 20 is letter T, U is 21 is U, 18 is R, 14 is N, 27 now is the spacing, right? So in the alphabetical table, we already mentioned at the beginning that for the spacing, either you use 0 or 27, right? So in this case, I use 27. Now 8 is H, 15 is O, 13 is M, 5 is E, and 27 is the spacing again. So the message that we receive is return home, right? So the message received is return return home. Okay. So I thought this is a very fun application for matrix multiplication or matrix operations in general, and also help us to actually see the usefulness of finding the inverse of the matrix and apply matrix operations on some real world applications. I mean, certainly in real life situations, the message going to be longer, the matrix that you need to do is going to be bigger. All right, it's not a 2x2 matrix or 3x3 matrix. This can be a 10x10 matrix, right? But I thought this is a very fun applications to know. Okay, so that's it for me. And please let me know if you have any questions. Thank you.